Hey, this is MAT 221. This is Mrs. Johnson. This is Calculus 1. We're in our second video of section 2.4 on continuity in calculus. So we looked at this function here. Then we were looking at part C. If we look at part C and A are very common to each other. If you look, this is just the rational function. This is the rational function plus a point on the curve. So it's saying when x equals 2, the value of the function equals 1. So this part of the function looks a lot like this graph we have in part A. But it's saying when x equals 1, when x equals 2, we're going to put a point on the curve at x equals 1. So if you look at this curve, it would look like this, and then it would have a hole, but then at x equals 2, there would be a point right here at 1. Does that remove that hole? Does that remove that discontinuity? It actually doesn't. So let's actually look at that graph. That graph looks like this. So it has the same rational function with the hole in it, but this point that it put here at x equals 2 actually didn't fill in the hole. In order to make that actually get filled in, the value of the function would have to be 3. So I still have discontinuity, and I still have jump discontinuity, because again, there is a bullet hole in the function with a dot somewhere else. That's called removable discontinuity. This last function that we look at in D is called the greatest integer function. It's actually the step function. Looks something like this. So if we look at this function, we'd say, okay, does that function have discontinuity? Well, absolutely. Every time I have to lift my pen from the page, I definitely have discontinuity every single time. Notice there's a big gap in the domain, in the range. So here I have what's called jump discontinuity at every positive and negative integer. All right, so let's go through some facts we know just because we're smart. And we know from pre-calculus a lot of the functions that we studied, that library of functions that we have in our brains. We know that all polynomial functions are going to be continuous everywhere. That's linear, quadratic, cubic, quartic, quintic, and so forth. All going to be continuous. I never have to lift my pen from the page. We also know that the sine function, the cosine function, and the inverse tangent function are also continuous functions. There's the sine function and the cosine function. Inverse tan, by the way, is one branch of the tangent function kind of shifted on its side, reflected over the line y equals x. All continuous functions. We know that all exponential functions and natural log functions are going to be continuous. We know exponential growth and decay, and we know the log functions. All continuous functions will never have any holes or jumps or vertical asymptotes. So, some more facts that we know is that continuous functions can be added together. They can be subtracted from each other. They can be multiplied. They can be divided, so long as our denominator is not 0, and be multiplied by some constant. And all of these new functions will remain continuous functions. Also, composites of continuous functions are continuous. All right, so we have a whole bunch of functions in our repertoire that we already know are continuous, and we know that we can add them, subtract them, multiply them, divide them, and multiply by a constant, or compose them and still remain constant. Still remain continuous. So here's some examples. If I gave you the composite function y equals sine of x squared. Now we know the sine function is continuous. We know the x squared function is continuous. This is actually what the function looks like, and you notice it is also continuous. It's kind of funky, but still continuous. Here again, the cosine function is continuous. The absolute value function, we should have added that one in there too. The absolute value function is also continuous. When we put them together and compose them, we still have a continuous function. All right, a really important theorem that we have to talk about when we talk about continuity is called the intermediate value theorem. And the intermediate value theorem says this: if a function is continuous between the points A and B, then it will take on every value between f of A and f of B. All right, so let's see what this function is actually saying. It's saying, first of all, I have a continuous function from A to B. Now, I don't know what that function is, but I know it's continuous. No breaks, no jumps, no vertical asymptotes between x equals A and x equals B. What this theorem says that the function must take on every value, which means it must have every y value between the y value at A and the y value at B. So notice here would be the y value at A, here would be the y value at B. What this function is saying is every single y value between those two y values has to be hit at least once between A and B if f is a continuous function. Now, notice it may hit that y value more than once. For instance, if I look at f at A, it actually hits it, looks like 3 times, here and here and here. It looks like it hits that y value 3 times. But all this is saying with the intermediate value theorem is that if I have a value of a function here at this endpoint, a y value, and I have a value of at this endpoint, a y value at B, then if I have a continuous function, all of these y values between f at A and f at B have to be hit at least once if I have a continuous function. Because the function is continuous, it must take on every y value between f of A and f of B. Now we said it may take on those values more than once, but the intermediate value theorem is saying it has to take on at least once if I have a continuous function. So pretty intuitive. This is affectionately known as the IVT, by the way. A little story about the IVT that was actually brought into court many years ago when EasyPass was first being tested in New Jersey. And they brought it into court to prove that people were speeding, because if they went through one EasyPass toll and then another EasyPass toll on a continuous road, and they went through the time it took to go through this one to this one and what the speed limit was, and then they said, well, you must have been speeding between point A and point B to get from point A and point B in that amount of time. And then they brought these mathematicians in to use the intermediate value theorem to show why that had to be true. However, although this was used in court, it was thrown out because the EasyPass people were told that you have to catch someone in the act of speeding. You can't just do the math to actually catch them. So here are some more notes. Here we have, note that a value of the value of the function can be taken on once as in part A, or more than once. So notice here I'd say a value can take on just once, right, between f at A and f at B, or it can take that value on several times during that interval from A to B. What the intermediate value theorem is saying, it has to occur at least once in that interval if the function is continuous. Now, what Rolls did, a famous mathematician, was he added a little bit to this to actually get Rolls' theorem, which says, additionally, suppose that f is continuous on A to B, and f at A and f at B have opposite signs. In other words, the output at A is negative and the output at B is positive, or vice versa. So the output at A and the output at B have opposite signs. Then Rolls says, then there's got to be at least one number, C, in the interval from A to B, where the value of the function will equal 0. In other words, in order to get from this endpoint to this endpoint, if one endpoint is negative output and one endpoint is a positive output, and I have a continuous function, I have to go through the x-axis at least once. In other words, I have to have at least 1 0 for the value of the function. Now, this is called Rolls' theorem, and it's actually the theorem that is calculated on your calculator when you try to get the zeros of a function. You actually have to have a sign change. Sometimes you do this on your calculator and it'll say no sign changed when you're trying to find the 0. So they actually use Rolls' theorem to actually use it on computations for math on Mathematica and on your calculator. All right, so let's do a couple of examples to investigate the continuity of a function. Okay, what does this function look like? What do we know about this function? This has a constant over a linear function. We know it's a rational function. We're talking about on the interval from x equals 0 to x equals 3. We look at the denominator and say, okay, there's going to be a problem at x equals 2. And from what we know already about rational functions, we know that there's no linear factor that's canceling in the numerator. So at x equals 2, we're going to have a vertical asymptote. And x equals 2 is in the domain that we're looking at. Now, if we were looking at a domain that didn't include x equals 2, we could say the function is continuous on that domain. However, in this case, we're looking at a function here that 2 is in the domain, and we know there probably will be a vertical asymptote there. There actually is a vertical asymptote there. So we see the rational function will be undefined at x equals 2, and this value is in the interval. Therefore, this function is not continuous on the given interval. There will be a vertical asymptote at x equals 2. Therefore, we have infinite discontinuity. We have infinite discontinuity at x equals 2. Here's the graph of the function. Now, we would only look from x equals 0 to x equals 3, so we're only looking in this domain, but we still have infinite discontinuity at x equals 2. What about this function? Let's investigate its continuity. Well, let's see. I have a function, I have a cosine function, which, because we're smart, we know cosine functions are continuous everywhere. And it's being added to a cubic function, a power function actually, a cubic function, 2 times x to the third. This is continuous everywhere. This is continuous everywhere. We're adding two continuous functions everywhere. It really doesn't even matter what interval we're looking on, although we're looking on the interval from 0 to pi. This function is continuous everywhere, because if we add two continuous functions to each other, we continue to have a continuous function. So we know that the trigonometric function is continuous. We know the cubic power function is continuous. So therefore, the sum of the two functions must also be continuous on any given interval. And then I graphed it, and I saw this is definitely continuous from 0 to pi. All right, so that finishes up section 2.4 as far as our PowerPoint is concerned. I will put up a couple more videos going through some of the worksheets in your packet so that we can look at those answers of how we can look at limits and use the intermediate value theorem.